Welcome to the Joy of Math with Mr. G. I am Mr. G. This is Lesson 1 of 9th grade, Unit 1. The unit is all about patterns. So let's look at this pattern of tiles shown here. And just so you know, this video and every other video in this playlist, all of the lessons can be found at Open Up Resources. I am not affiliated with this curriculum, but it is free, it is online, and it is amazing. So I just want to share it with you in case there's anyone out there who's in school, struggling in school, out of school, or just curious about what this math looks like. So we're starting at the beginning of 9th grade right now. And this is a pattern of tiles made with a 5x5 square of white tiles. That's inside here, 1, 2, 3, 4, 5. So there's a 5x5 square inside, surrounded by a border with alternating colored squares. You see here there's alternating green and white. Show how you would group the tiles to quickly count the number of squares in the pattern. So I want you to think about how would you count the number of squares that are colored in this pattern. And then I want you to pause the video, type it in the comments, and let me know. I love reading comments. I love thinking about how students think about math. And I have some ideas here that I wanted to show you and think about, and I wonder if this is how you thought of these. The first way that I thought about counting these looks like this. I kind of thought, okay, well, I have a large section here at the top that has 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I have 9 down here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have like 2 9s. And then over here, I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then I have 2 5s. So there's 18 and 10. That's 28. That's one way that I saw that. So let's call this method A. I'm going to come up with a cooler name for it in a moment, but, you know, A for now. And then another method that I saw is right here. I thought about, well, what if I had 4 corners? Because I noticed that in the corners, there were 4 here. Let me see if I can get a little zoom action here for you. Let's go. Let's get the technology working. Look at that. You see? So there's 4 sides and 4 corners. Let's call these the corners. And then let's call these the sides. The sides have 1, 2, 3, 4, 5 colored in blocks. So that's what this 4 times 5 is here. And this 4 times 2 over here is the 4 groups of 2. So 20 and then 8, 28. Okay. So another way of finding 28 that is the same total value, but a different way of grouping and counting these. Let's see if we have a couple more. What about this method here? I really like this one. So if I think of this whole square as 9 times 9, that would be 81. So just the whole big gigantic square, that would be 81. And then if I subtract this 5 by 5 in here, if I subtract that 25, I would be left with 56. That's 56 is this border around the outside because I took the whole square and subtracted this little square inside. But now down here, if I divide that 56 by 2, because every other one of these is colored in this checkered pattern, then there's 28. Wow, that's a third way to find 28. Oh my goodness gracious. I'm going to add it to my pile of strategies, and I have one more here for you. I know you thought I only had 3. I do not. I have 4. This one says that we have 4 equal sides. So let's take a look at these 4 equal sides. We have this side here. 1, 2, 3, 4, 5, 6, 7. There's 7 here. There's 7 here, there's 7 here, and there's 7 here. There's 7 on each side. This one took a second for me to see, so if you don't see it, I kind of totally understand. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So 4 groups of those 7. So also equals 28. So no matter how we count it, this 5 by 5 square surrounded by a border with alternating colored squares has 28 total inside of it. 28 total inside. Very cool. What I want to think about is how we could use those strategies for a similar pattern. So now, again, all of these problems come from Open Up Resources. This is lesson number 1 of the Patterns unit for 9th grade. Let's read it together. It says, in preparation for going back to school, eek, Ugh. The school administration plans to replace the tile in the cafeteria. That's very nice of them. Don't use asbestos. They would like to have a checkerboard pattern, of course, because we're talking about checkerboard, of 2 rows wide to surround the tables and serving carts. Below is an example of the border that the administration is thinking of using to surround a 6 by 6 square of white tiles. Okay, so now we have inside here, we have 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6 this way. We've got our 6 by 6 tiles all across here, and they're asking us to count how many. And what I would love to do is take us through those 4 strategies we just looked at for the 5 by 5 square. This one. And see if we can use them here. See, it's a little bit bigger. See, that square on the inside is a little bit bigger. Over here we had 1, 2, 3, 4, 5 by 5 square. And over here we have a 6 by 6 square inside. So the total is going to be more than 28. Because over here we had 28 green squares. We're going to need more than 28 green squares. So let's see if we can figure that out exactly. And I know what you're thinking. Man, I wish that you had come prepared and printed out a number of these together. I have. Look at these. Printed them out for us. Ready to go. Okay. Yes. Let us see. I think I need to change this camera angle just a scotch down. Yes. There we go. Okay. So the first strategy that we looked at together for counting the 5 by 5 square was this one here. So we had a 9 across the top and a 9 across the bottom, and then we had 2 groups of 5 here. Let's see if I could make that happen over here and see what it would look like. I'm going to color these in. So I'm going to color in the top here. Let's go. This big rectangle up here. Very nice. And this rectangle down here. That seems to match the big rectangle I did over here and the rectangle I did over here. And these had 9 green squares in each. I don't know if it's true over here, so let us count together, shall we? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, now we have 10 up top and 10 down here. Okay, so let's call this, we called this A. Let's say that we could write this as 2 groups of 10, because I have 1 group of 10 here, 1 group of 10 down here, and then I'm going to count what's on the side. Let me get a different color. Let's go with green. If you're colorblind, I'm really sorry. I color code a lot, and I'm trying to think of a way to deal with color coding that does not leave out people who are colorblind. So I try to pick things that have different hues. I don't know if I did a good job here. I think I picked 2 things that look almost identical. So that's my bad. I'll try to do better next time. Let's count these side rectangles here. I had, over here it was 1, 2, 3, 4, 5. Let's see how many are colored in here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so I have 2 groups of 10 and 2 groups of 6. If you're wondering why I'm writing these as multiplication, it's because I'm having 2 groups of 10. So I have 2 10s and 2 6s. So that would equal, that's 20 plus 12. That would equal 32. So it seems that I have 32 here. Let's see if I could use our other strategies to get the same thing. Okay, so I'm going to put these 2 over here. Sit. Next, let's go. What was our second strategy that we discussed? It was our 4 sides and 4 corners move. So let's take a look at that. So if I have 4 sides and 4 corners, how could I do that on this over here? Well, let's color code our original. Let's say I'm going to do let's do the 4 corners first. 1, 2, 3, 4. Do we have the same corners here? Let's see. This is a corner. There's a corner, okay. Then I've got another corner over here, another corner over here, another corner over here. The corners kind of look the same, which is interesting. So I had 4 times 2 over here because I had 4 groups of 2, and I have 4 groups of 2 over here. So we'll call this strategy B. For strategy B, I have 4 groups of 2 in my corners here. And now let's see what the sides are. The sides over here, I'll need a different color. Hopefully that'll be a little bit more different. Let's go light blue. Okay. Over here we had 5 on each side. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's see over here. 1, 2, 3, 4, 5, 6, I believe. 1, 2, 3, 4, 5, 6. And we also had the ones up top over here. So I gotta do the top. So we're counting this the same way as we counted. And think about how I might write this. I'm gonna write this as 4 times 2. And then what do I have? I have 4 groups of what? Let's count the blue rectangles here. 1, 2, 3, 4, 5, 6. Is that the same for all of them? 1, 2, 3, 4, 5, 6. Yes, it's the same for all of them. So let's calculate that up and see what we get. 4 times 2 is 8. So that means that in the corners here I have 1, 2, 3, 4, 5, 6, 7, 8. That makes sense. Plus 4 times 6. 6, 12, 18, 24. And 8 plus 24 is 32. So same thing we got up here. So looks like we're doing things the right way because we got them done. Let's keep going. Next we did the area of the outer square, and then we subtracted the area of this inner square. So in this case we had like a big 9 by 9 square, and we subtracted the 5 by 5 square inside. So let's do that here. Let's count what our large square is. I'm going to call this strategy C. Big square minus middle square. We'll call that big square minus middle square. Because I'm taking the big square, taking away the middle square, seeing what we're left over with. I don't think it's 9 by 9 here. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we have a 10 by 10 outside square. So we're going to do 10 times 10 minus 1, 2, 3, 4, 5, 6. Oh yeah, it's a 6 by 6 square inside. I forgot. 6 by 6. And then we'll divide that whole thing by 2. See how I just wrote the whole thing by 2? That's the same thing that they did over here. They just calculated this value first and then divided by 2. I'm going to do that same thing over here. So 10 times 10 is 100. So this whole thing has 100 squares in it. It's a 10 by 10 square. I'm going to subtract these in here. That's 36. So let's subtract those. So 100 minus 36 is, what's that? 100 minus 36 equals... It's not 70 because 100 minus 30 is 70, so it would be 64. And then 64 divided by 2 would equal 32. Oh, that makes sense because that's what we got before. So again, so there's 100 in the whole thing. We subtracted these 36, leaving us with 64 around the outside, and we divided by 2 because every other one is colored in. So I don't want to count everyone around the border. I only want to count half of them. So that's 32. Wow, that's very, very cool. I like that strategy a lot. I think that might be my favorite so far. But that doesn't mean we're going to do the last one. Okay, so here they kind of counted the equal sides. So I'm going to do that cross in the middle again to see the equal sides that we get. So, like, great. Okay, well, obviously that is not cooperating. Let's go to the Bic Crystal. The Bic Crystal is a pen that, you know, doesn't get talked about a lot in pen communities, but it's beautiful. Now what did I do? Okay, wait, but how do we, this is a mess because we're cutting them in half now. Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 7.5, and 8. 1/2, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8. So we've got 4 groups of 8 here. So 4 times 8 equals 32. Wouldn't you know it? Oh my gosh, it's the same amount that we got before. Okay, so no matter how we calculated these, we all came to the same value of 32. That is unbelievable, which tells me that all of these expressions here are called equivalent expressions. Let's take a look at which equivalent expressions we came up with here so far today. And this, okay, you know what? It's it's empty. The ink's empty. It's not its fault. It's not its fault. It just needs more. It just needs more ink. You know, I have ink for it. Equivalent expressions. That's a super important vocabulary word in 9th grade math when you talk about expressions that are equivalent to each other. So 2 times 10 plus 2 times 6, that is an expression. It was this one. 2 times 10 plus 2 times 6. That has the same value as 4 times 2 plus 4 times 6. So this is equivalent to 4 times 2 plus 4 times 6. And we just proved that with these patterns here. So the way that you group things together can change the way that your math looks, but it's not going to change the value of your expressions. Those are going to be equivalent expressions. Okay. Let's see if we can generalize these patterns here. Because the contractor who was hired to lay the tile in the cafeteria is trying to generalize a way to calculate the number of colored tiles needed for a checkerboard border surrounded a square of tiles with any dimensions. So we did a 5 by 5 square and we did a 6 by 6 square. They're trying to think, hey, I don't want to have to calculate this every time I have a new square inside. I want to generalize this for any square. So let's say we have an n by n square inside. How would we calculate the every other checkerboard pattern we have here? The contractor started sketching the square. Since he wants the diagram to work for any number of tiles in the middle square, he just called the side length n for the number of tiles on that side. Use the same counting strategy that you used for the 5 by 5 or the 6 by 6 square to find an expression. So I'm going to start with my favorite one. My favorite one that we did so far was this strategy here. When we had a 5 by 5 square, let's talk about what we did. So let's just generalize. Let's see if we can see some patterns here. So when we had a 5 by 5 square, what did we do? We did 9 times 9 minus 5 times 5, and then we divided that by 2. Okay. What about when we had a 6 by 6 square? For this square here, we did 10 times 10, and then subtracted that inner square, which is 6 by 6, and then divided by 2. So for an n by n square, we have to think about what patterns there are that we notice between the dimensions of the square and our way of figuring it out. So the first pattern I notice is that in both expressions, we divide by 2. That's the same. So in our n by n expression, we're going to have a divide by 2. We also have two things that are being subtracted one from another in both. So we have 9 times 9 minus 5 times 5. We have 10 times 10 minus 6 by 6. And that's because in both strategies, we are starting with one square and subtracting the inner square, and then dividing it by 2. So that shape is going to be the same for an n by n. Do you notice anything else about these expressions? I noticed something really interesting. I noticed that when we had a 5 by 5 square inside, we subtracted that 5 by 5 square. And when we had a 6 by 6 square, we subtracted that 6 by 6 square inside. So the size of the square inside is always what we were subtracting. So instead of having 5 times 5 or 6 times 6 written here, for an n by n square, I'm going to write n by n. Because no matter what this square is on the inside, I'm going to subtract that from the whole square. So it's n by n. Now we got to think about this big square. How big is this square going to be if the inside square is n? Well, it's going to be bigger than n, so it's going to be n plus something. But I don't know plus what. Let's look at what we had. When we had a 5 by 5 square inside here, our bigger square was 1, 2, 3, 4, 5, 6, 7, 8, 9. It was 9. And it looks like we added 2 to the top and 2 to the bottom, and that's 4 longer. So it's the big square is 4 longer than the inside square here. And what about when we had 6 by 6? Well, this inside square is 1, 2, 3, 4, 5, 6. And then we add 2 more to this bottom and 2 more to that top. So the outside becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's always 4 more. The outside square is always 4 longer than the inside square because you have 2 rows on top and 2 rows on bottom and on the sides as well. So I'm going to generalize that as n plus 2 minus n times n. So this expression is one way that we could generalize our counting strategy. Do you think we could generalize it for another counting strategy? We absolutely could. We absolutely could. Thank you for asking. How could I generalize it for this one? For B. In this one, we counted our corners. And then we counted these. How could we generalize this? And then also, how could we generalize this strategy? Here, where we had a rectangle up top and a rectangle on the bottom. And how could we generalize, where's our other strategy? How could we generalize this one, where we had 4 groups multiplied by something? What do you think? Let me know in the comments. This is B. How would you do strategy B for an n by n? How would you do strategy A for an n by n? And how would you do strategy D for an n by n? I showed you strategy C, our big square minus middle square. How would you do either of these generally for an n by n square? Let me know in the comments, and thank you so much for attending the first day of 9th grade. This has been the Joy of Math. I have been Mr. Gentiles. That's Babs Ross. He's inspired by Bob Ross, my favorite teacher. Thank you. If you like this video, please let me know in the comments. I would love to continue teaching 9th grade. I'm going to make one video of each grade, post them on YouTube, and see which video gets the best results, and I will continue that unit of study after that. This was 9th grade. Let me know in the comments if you want me to continue. Thank you so much. Have a good night.